So it's the integral of the square root of 1 minus cosine of 2x over 5 all over 2 dx. And the idea for a problem like this, if you see a problem like this, the expectation, I think, is that you remember the identity, the half angle identity, in this case for sine, is that sine squared of to 1 minus cosine of 2 theta all over 2. That's the idea here, is that we're supposed to use that identity. So then, in this particular expression here, what's playing the role of theta? Well, I want this to be cosine of 2 theta. Since that's 2x over 5, theta is going to be played by the x over 5. So that sine squared of x over 5 is equal to 1 minus cosine of 2x over 5, all over 2. So then I can rewrite this integral as the integral from 0 to 15 pi over 2 of the square root of sine squared of x over 5. That is how we are meant to do a problem like this, I think. You can make it more common. You could do other things, but this is probably the most straightforward way of doing this. And then now, I think the problem that's in the homework, you don't have to worry about the next part, but here, I don't have to worry about this. So I could do a U-Substitution. In fact, I might do it. I don't really want to do U-Substitution. Let's just simplify it. So this is equal to integral from 0 to 15 pi over 2. Now, it's not just sine of x over 5. It's the absolute value of sine of x over 5. Because this inside here is sometimes negative. If you're going from 0 to 15 pi over 2, you've got x over 5. 0 to 5 pi, which is 10 pi over 2, that's going to take x over 5 from 0 to pi. That's where this thing is positive. And then this inside is negative from 5 pi, which is 10 pi over 2, to 15 pi over 2. So we actually have to break this up. Oh, I'll remember that. Sine of 5x, sine of 9x. So we actually have to break this up as the integral from 0 to 5 pi of sine of x over 5. Again, 0 to 5 pi means x over 5 goes from 0 to pi. That's the first and second quadrant where sine is positive. And then the rest is from 5 pi to 15 pi over 2. 15 pi over 2 divided by 5 is 3 pi over 2, which is the end of the third quadrant. So this goes from the second quadrant to the third quadrant where sine is negative. So we need a negative sine of x over 5. How exciting. Questions about this? Okay, the rest is not too terrible. I mean, it's still kind of terrible. So we integrate sine, we get negative cosine, so I'm going to get negative cosine of x over 5 divided by 1/5, which means I'm multiplying by 5. It's really negative 5 cosine of x over 5 from 0 to 5 pi. Plus, integral of negative sine is positive cosine of x over 5. Again, dividing by 1/5, so multiplying by 5. From 5 pi to 15 pi over 2. All right, and now I have to plug in. Of course, I've run out of room. So, I guess I'll erase this part here. So we end up with plugging in 5 pi, cosine of pi is negative 1. So you get negative 5 times negative 1 minus, when I plug in 0, I get cosine of 0, which is just 1, plus 5 cosine of 5 pi over 2 over, that's a 15 out of 5. Cosine of 15 pi over 2 over 5 is 3 pi over 2. Cosine of 3 pi over 2 is 0. And 5 pi over 5 is pi. Cosine of pi is -1. So minus -1. Okay, let's see what we get. We get -5 times -2, which is 10, plus 5 times negative, that can't, that's a minus 1. That's 5 times 1, which is 15. Want to point out that if we just integrated this kind of the wrong way and did from here to here, we would have ended up with 0 minus 5, or minus 5, which would have given us just 5. We would have totally been missing out on a good portion of this graph. Yeah, kind of neat. Okay. So the real thing to, like, I wouldn't sweat this part too much. I was just kind of adding that on to make it extra hard. But the part you should really remember is the fact that 1 minus cosine of 2 times an angle all over 2 is equal to sine squared of just 1 times that angle. And if it was 1 plus cosine of 2x over 5 all over 2, that would be, instead of sine squared of x over 5, it would be cosine squared of x over 5. So there's an important trig identity to come up. Okay, now for a trig identity that I don't know at all. Meaning I'm going to look at a thing. So I'm going to erase this because I want to, I've got some stuff written on the other side of this. I'm saving. So let's look at this next one. So I've already forgotten. I think it was sine of 9x times sine of 5x. There's a way to actually figure out what this is supposed to equal. You might even be able to do this using integration by parts. It's not the way I've learned to do it. There's a trig identity for this. There's an identity that says if you have sine of an angle times sine of another angle, it's equal to, and I'm really just looking at this list I've got here, it's equal to 1/2 cosine of A minus B minus 1/2 cosine of A plus B. So this ends up equaling the integral of 1/2 cosine of, I'm calling this A and this B, so it's 9x minus 5x, so 4x minus 1/2 cosine of A plus B, which is 14x. That's kind of it. And then we can integrate this. So we get 1/2. The integral of cosine is negative sine, so you get negative sine of 4x over 4 minus 1/2. The integral of cosine is negative sine, so it's going to be a plus 1/2 sine of 14x over 14. And then you could probably do a little, right? I don't think you would simplify this, but you could. It could be sine of 14x over 28 minus sine of 4x over 8. Yeah, that's, yeah. I'm not in love with this problem. Not because it's not, I mean, it's fine what we did. It's just, I don't know how you would do this other than just looking up the identity for it. Yeah. Anyone have any thoughts about this? Any comments about this? It's okay if you don't. If your teacher might have done this a different way, that is also okay. Right. That's all I have to say about that one then. Let me take a look back at my list here and see what else I've got. Where'd my giant list go? All right, one sec. Okay. So we could do more powers of trig things. I don't really think that's what we need to do necessarily. I'll just remind people. I'll do one, maybe. So it's something like the integral of, oh, there is, yeah, okay, there's two problems we should do. If we had something like the integral of secant to the 6x tangent to the 6x. We have to decide if we're going to let UBC. Oh, to bring the board a little more forward. Yeah, I can probably scoot a little more forward. One sec. Oh, gross. Okay. Hopefully that's a little bit better. Also, I just found some cat vomit, which is really lovely. You guys all want to know that. All right, so we have to pick a u, and again, we want to make the u choice so that after we find du and take that part out, the non-u trig function should have an even amount left over. So I don't want to pick u equal to secant, because then my not u thing is tangent, my du is secant tangent, and after I take away one tangent, I'll have an odd number of tangents left over. So here I want to pick u equal to tangent, because the du will be the derivative, which is secant squared. And when I take away the secant squared from the secant to the 6th, I'll have an even number of secants left over. So I can write this as the integral of secant to the 4th x times tangent to the 6th x times secant squared x dx. That's my du. Tangent to the 6th is just u to the 6th. And secant to the 4th, that's where we're going to have to use our trig identity. We know that I tan and get sexy. We have secant to the 4th. Don't update. Go away. Sorry. There. Okay. We have secant to the 4th, so we have to square both sides. So secant to the 4th is equal to this thing squared. Now tangent is equal to u. So this is really 1 plus u squared squared. So when we write this out, it's going to be, we're going to be integrating 1 plus u squared, which I'm going to multiply out. It's going to be 1 plus 2u squared plus u to the 4th times u to the 6th du. We have to multiply it out before we can integrate it. So we're going to get the integral of u to the 6th plus 2u to the 8th plus u to the 10th du. And then finally, we have to differentiate each thing. So u to the 7th over 7 plus 2u to the 9th over 9 plus u to the 11th over 11 plus c. And then finally, we plug back in that u is equal to secant. Sorry, u is equal to tangent. So you end up with tangent to the 7th x over 7 plus 2 tangent to the 9th x over 9 plus tangent to the 11th x over 11 plus c. Good times. Okay. There is, I will remind everybody, I'm not going to do it, but if you have even powers of sine and cosine, you have to do the identity that we just talked about, where sine squared is 1 minus cosine of 2x over 2, and cosine squared is 1 plus cosine of 2x over 2. So if you have like sine to the 4th, you have to use that identity twice. If you have cosine to the 4th, you have to use that identity twice. But what I want to talk about for a moment is a very special trig integral. When I was teaching Calc 2 at a different university, this is a question I would always put on the test. I thought it was definitely a question that was worth asking. So the question I want to ask is the integral of secant cubed x dx. And, and unlike, so, you know, I don't know if everybody took the quiz. On the quiz I asked everyone to, I think it was the integral tangent to the 4th, or maybe, no, it was secant to the 4th. And I told you all to make the trig substitution of letting u equal tangent, because then your du is secant squared, and the leftover secant squared can be turned into 1 plus tangent squared. Not so much an option here. So here, for secant cubed, or really, this is kind of the least terrible version of this kind of problem, for any odd power of secant times an even power of tangent, which we have because they're tangent to the 0. For any odd power of secant times an even power of tangent, there is a method to the madness. And the method is you have to do both an integration by parts and use a trig identity. And it actually doesn't really matter what order you do it in. I am personally partial to doing the integration by parts first. So let's do integration by parts. So we want to pick a u and the dv that multiply to be secant cubed x dx. We want to pick u, well, I mean, really we've only got trig things, but we want to pick dv to be part of this that's easy to integrate. So let me ask you guys, should dv be secant or secant squared or secant cubed? Which of those is the easiest to anti-differentiate? Secant or secant squared or secant cubed? Yeah, secant squared, right? We know that secant squared is the derivative of tangent. So you always want to pick your dv to be kind of the easiest thing that we can still integrate. If we pick dv equal to secant, the antiderivative of secant is the natural log of secant plus tangent in absolute value, which we don't want to do. U, on the other hand, is going to be secant. So then my derivative of secant is secant x tangent x dx. My antiderivative of secant squared is tangent. Okay, let's use the integration by parts. So this is going to be equal to uv minus the integral of v du. So this is going to equal secant x tangent x minus the integral of tangent times secant x tangent x dx. Okay, I'm going to do a little bit of rewriting. I'm going to rewrite this as tangent times tangent is tangent squared. So 0 of tangent squared x secant x dx. Now, let me warn you, you don't want to go the wrong way here. If you try doing integration by parts again, the natural choice for your dv is secant tangent, and then your u is tangent. And that's fine, but what you'll end up doing is you'll end up undoing all the work you just did and getting back to the integral of secant cubed, which is true. The integral of secant cubed is equal to the integral of secant cubed. It's not helpful. Instead, we're going to use a trig identity. We're going to use the fact that, in fact, the one we just used, we know that 1 plus tangent squared x equals secant squared x. So we know that tangent squared x equals secant squared x minus 1. So I'm going to replace tangent squared x with secant squared x minus 1. This is now equal to still secant x times tangent x minus the integral of tangent squared, which is secant squared x minus 1 times secant x dx. Okay, let's simplify a bit. This is going to be equal to secant x tangent x minus, so when I multiply this out, when I distribute the secant x here, secant squared times secant is secant cubed, so it's the integral of secant cubed x. And then minus 1 times secant is minus secant x dx. Okay, I'm going to save a little bit of space here. No, I'm not. So let's see. This is going to be equal to secant x tangent x. I'm going to break this up into two integrals. It's going to be minus the integral of secant cubed x dx. And the minus of minus is going to be plus the integral of secant x. Okay, so here's what I've got. I've got the integral of secant cubed is equal to secant x tangent x minus the integral of secant cubed plus the integral of secant. I'm going to add this to both sides. Meaning I'm going to add an integral of secant cubed here. I'm going to add an integral of secant cubed here. So what do I get? Well, I get 2 times the integral of secant cubed x dx. This is very similar to the integral of e to the x sine x, where we do integration by parts twice and then get the same thing we started with and add it over to the other side. We're just not doing integration by parts twice here. So I do that, and I've got secant tangent, or I should say secant x tangent x, plus the integral of secant x is the natural log of the absolute value of secant x plus tangent x. Finally, we divide both sides by 2. So that the integral of secant cubed x dx is equal to 1/2 of all of this. It's 1/2 of secant x tangent x plus the natural log of the absolute value of secant x plus tangent x plus c. That's how you integrate secant cubed. And that's kind of the process for integrating any odd power of secant and an even power of tangent. So another question you might see someone ask you at some point, which requires pretty much the same amount of effort, is the integral of secant x times tangent squared x. If you had to do that problem, you would want to start off by, I would want to start off by letting dv be secant tangent and u equaling tangent. And then you would do integration by parts, and then you get some integral, and you do a trig in the integral, and you end up back where you start with eventually. Okay. So those are the only powers of trig functions I really want to talk about. What I really want to go to now is we're talking about trig substitution. So yeah. So someone in their reflection said something that I thought was kind of useful. Usually they write the triangle first. And I've always been a person who's said what the substitution was first, but it kind of makes sense when I thought about it to really write the triangle first. So if we see a square root of a squared minus x squared, we know this is going to be our triangle because we know the third side has to be that. If you use the Pythagorean theorem, this side has to be the square root of a squared. So I made yeah, except I did it wrong. Sorry. Because I'm a dork. I wrote the wrong things. This is supposed to be x and a, and this is supposed to be. Sorry about that. So, they have to go like this because you need this squared plus this squared to add to that squared. Another way I think about it is we need the trig identities to work. Right? I know that I need sine of theta to be x over a. Or, if you prefer, a sine theta to equal x. Because when you plug in a sine theta here for x, you get a squared minus a squared sine squared. If you factor out the a squared, square root of a squared is a. You get a times the square root of 1 minus sine squared theta. And the thing is, 1 minus sine squared is equal to cosine squared. So the whole reason we're making this choice, we're drawing this triangle, is so that if you see this, you get to replace that with a cosine theta. You get to get rid of the square root. That is the whole kind of purpose of doing these trig substitutions, is to eliminate the radical so we don't have to deal with it anymore. And the same is true for the rest of these. And hopefully I have enough room. I think I have enough room to write this. Sure. Let me just. So here, I have a squared plus x squared. That third side is going to be the square root of a squared plus x squared. And I'm seeing that tangent of theta is equal to x over a. Or if you prefer, a tangent theta is equal to x. And if we plug that in for x, our square root of a squared plus x squared becomes the square root of a squared plus a squared tangent squared. Again, we can factor out the a squared which comes out as a, and this is going to be a times the square root of 1 plus tangent squared, but we know that 1 plus tangent squared theta is secant squared theta, so it's just a times secant theta. Same deal here, right? We're making this triangle choice because we know that this third side needs to be the square root of a squared minus, x squared minus a squared. Because this squared plus this squared gives you that squared. So basically, when you see the square root thing, you have to write the triangle so that the unknown side is the square root thing. It's still not super, I've just thought about this, so I'm probably not saying it as maybe amazingly as it could be said. I don't remember who wrote it in the reflection, but hopefully I'm kind of hitting on the thing that person said. Here we have x over a is equal to secant theta, or a times secant theta is equal to x. Right, we're always trying to solve for x. And so then we put that in there, we get the square root of x squared minus a squared is the square root of a squared secant squared minus a squared. Factor out the a squared, you're left with an a square root of secant squared theta minus 1. And secant squared minus 1 is tangent squared. This is a tangent theta. So, in our integrals, if we see a square root of a squared minus x squared, we're going to be able to replace it with an a cosine theta. If we see a square root of a squared plus x squared, we're going to be able to replace it with an a secant theta. If we have the square root of x squared minus a squared, we're going to replace that with a tangent theta. Now, I still think it's good to write out the work, but this is really the idea that's happening. Let's look at some examples. I will also say, I'm going to go back to this for 1 second. Trig substitution is where I think there's a really nice connection between the inverse trig derivatives and what you're doing here. I know, in fact, let me write them down here and then we'll go back. I know that the derivative of the inverse sine is 1 over the square root of 1 minus x squared. I know that the derivative of the inverse tangent is 1 over 1 plus x squared. And I know the derivative of inverse secant is 1 over the opposite value of x squared minus 1. Look, when you see something minus x squared, you choose sine for x. When you see something plus x squared, you choose tangent for x. And when you see x squared minus something, you pick secant for x. There's a very nice correspondence here that I would encourage you all to kind of make part of yourself. That's to feel in your soul. If there's probably a better way to say that. So trig substitutions. So what if I want to do the integral of, let's just make it straightforward, the square root of 4 minus x squared dx. Okay, I'm not going to lie, I do the trig substitution first. I'm definitely thinking, so I'm seeing that 4 minus x squared and I'm thinking, oh, I need a sine. I need x to be 2 sine theta. As much as I would like to pretend I draw the triangle first, I don't. The triangle here, I know, yeah, that's really kind of, I really don't think about it that way. What I really do is I think about this. I think, even though I know I need this, I have this. Sine of theta is x over 2. So that's x, that's 2, and that's the square root of 4 minus x squared. The nice thing about this triangle is the third side is always the side you need it to be. So then we're going to replace the, there's something really important here. Let me make a mistake, and then we'll see the important thing. So I'm going to get the square root of 4 minus x squared. So I'm going to get the integral of the square root of 4 minus 4 sine squared theta, which is equal to the integral of the square root of 4 times 1 minus sine squared theta, which is equal to, sorry, one sec. Yeah, fine. The integral of 2 square root of 1 minus sine squared is the square root of cosine squared, which is just cosine theta. And I've made a really big error. Right, if I integrate this, I'm going to get 2 sine theta, which is not the right answer. And the error I've made is I've completely ignored the dx here. Right? When you do any kind of substitution, whether it's a U-Substitution or Trig Substitution, we have to make sure, and I know I've really harped on this over the quarter, we have to make sure that the dx transforms into d whatever new variable we're using, which is why it's super important that you don't say sine of x here. You say sine of theta or sine of t or sine of any other variable other than what you're already using. So x is 2 sine theta, and differentiating both sides, dx is 2 cosine theta, d theta. So what I should actually have here, in addition to this part, is I should also have a 2 cosine theta d theta. I should also have here. Which means when I do this, I get, let me go up here, you get the integral of 2 times 2 is 4. Cosine theta times cosine theta is cosine squared theta. And now we have to use that identity for cosine squared. This is 1 plus cosine of 2 theta all over 2. Cancel a 2 here and a 2 here. So then I've got 2, integral of 1 is theta, integral of cosine 2 theta is sine 2 theta all over 2, plus c. Oh no. Oh no. Yeesh. So my answer is, well, not my answer, my almost answer is 2 theta plus sine of 2 theta. But my answer actually needs to be in terms of x. So if sine of theta, if x equals 2 sine theta, yeah. If sine of theta equals x over 2, then inverse sine of x over 2 equals theta. Okay. So that's fine for this part. Sine of 2 theta? I'm not just going to plug in. Here's what I'm not going to do. Even though it wouldn't be wrong, it's kind of wrong. I'm not going to write sine of 2 times inverse sine of x over 2. Here's what we're expected to do at this point. Sure. I don't even know where to write things. I guess I'll go to the other side. So here's what we've got. We've got our answer, which is 2 theta plus sine of 2 theta plus c. And we've got this. X over 2. So here's the thing. To solve this in what's considered an appropriate way, we have, right, sine of theta equals x over 2. Theta is the inverse sine of x over 2. Sine of 2 theta, there's a trig identity. Sine of 2 theta is 2 sine theta cosine theta. It's a double angle formula. And then we can say, oh yeah, 2 theta is 2 times the inverse sine of x over 2. And then sine of theta is x over 2. And cosine of theta is adjacent over hypotenuse, which is the the square root of 4 minus x squared over 2. And you can cancel 2 here and 2 here. You can get 2 inverse sine of x over 2 plus 1/2 x times the square root of 4 minus x squared plus c. A little bit tricky. So that's one example of a trig substitution. Let's do another. Let's do, sure. Trig substitutions can be challenging for sure. Where's the one I want? Yeah. So let's look at this one. Let's do the integral of dx over x times the square root of x squared plus 25. And I'm seeing, so I also know that when I've got a plus, it's tangent because a plus looks like a t. It's kind of dumb, but it's, you can't forget it. And then the other ones have subtraction signs which start with s, which either goes with sine or secant. It kind of works. Anyway, I have no idea how you see the triangle first. Because what I'm really seeing first is that I need x equal to 5 tangent theta. So the tangent of theta is x over 5. So that my triangle, if that's theta, there's x, there's 5. Sorry, that's not 5. But that's 5. And that's the square root of x squared plus 25. Okay, so now before we can do anything else, we also have to find dx. So dx is going to be the derivative here, which is just 5 secant squared theta d theta. All right, let's start replacing things. Dx is 5 secant squared theta d theta. X is 5 tangent theta. And square root of x squared plus 25. So I want to kind of make it as easy as possible. I really am just going to try and use a trig identity where I don't get this. So I can see that secant of theta is the square root of x squared plus 25 over 5. So 5 secant theta equals the square root of x squared plus 25. Or if you prefer, you can start with this and plug in that x is 5 tangent theta. And then you'll have the square root of 25 tangent squared plus 25. Factor out the 25. And you have the square root of tangent squared plus 1, which is just secant squared. So there's your 5 secant theta. Okay. Okay, now what? I can cancel some stuff. I can cancel a secant here and a secant there, a 5 here and a 5 here. So I'm left with 1/5 the integral of secant theta over tangent theta. Now what? So when I'm at a loss, I typically start thinking of things in terms of sine and cosine. So secant is 1 over cosine. Tangent is sine over cosine. So I can write this as 1/5 integral of sine over cosine over, 1 over cosine on top, sorry. 1 over cosine over sine over cosine. And the cosines cancel. So this is really the 1/5 the integral of 1 over sine, which is really 1/5 the integral of cosecant theta. And cosecant is an integral we're supposed to know. Yeah. There's just never enough room. There's never enough room. So the integral of cosecant is, there's actually two different kind of ways of writing it. I am partial to writing it as the positive natural log of cosecant theta minus cotangent theta in absolute value. It is equivalently equal to the negative natural log of cosecant theta plus cotangent theta. Either form was fine. And now we have to go back and look at the triangle. And say, okay, cosecant of theta, well, cosecant is the reciprocal of sine. Sine is x over square root of x squared plus 25. So cosecant is the square root of x squared plus 25 over x minus cotangent, which is not opposite or adjacent, but adjacent over opposite. And I would probably write that as one fraction. I would probably write it as this minus 5 all over x. And not that you absolutely have to use the triangle to figure out how to turn this back into x's, but it is definitely the easiest way to do things. So that's what I would recommend. Let's take a look at a couple other things. Oh yeah. You guys, your teachers like to ask you guys some really funky questions. Let's see, sure. Yeah. Let's look at this next one. Okay. Let's say I want to integrate x cubed over the square root of 1 minus x squared. Let's not make it too crazy. From 0 to 1/2. Okay. So here's the nice thing about a definite integral. We don't have to change back. Meaning if we do a trig substitution, we can also change our limits of integration so that we don't have to then change it back to being in terms of x. So I see a 1 minus x squared. I want my x to be sine theta. Because 1 minus sine squared is cosine squared. My triangle, which I still going to draw the triangle. I might need it. Never bad to have another triangle around. So sine of theta is opposite over hypotenuse. That's x over 1. And that third side is the thing that started the whole trig substitution in the first place. The thing in your integral should always show up in your triangle as the third unknown side. All right. So let's see what I've got here. X cubed is sine cubed theta. I need my dx. Dx is cosine theta. Which I should, cosine theta is d theta. Which I should. And the square root of 1 minus x squared is cosine theta. And you can either see it by plugging in sine, and 1 minus sine squared is cosine squared, and the square root is cosine. Or you can see it from the triangle. Cosine of theta is this over 1, which is just the square root of 1 minus sine squared. So then, we should change the limits of integration. This is the part that's a little bit challenging. So if I'm changing the limits of integration, those are x values. So if x equals 1/2, well, x is sine of theta. So I wrote my d theta in the wrong spot there. Apologies. So sine theta equals 1/2, which means theta is, well, where is sine equal to 1/2? It's when theta is pi over 6. Another way you can figure this out if you don't like doing what I just did is you could just say, oh yeah, theta has to be the inverse sine of 1/2, which is pi over 6. And if x is 0, well, that has to equal sine of theta, but sine of 0 is 0. So theta is 0 in this case. So that's what we're integrating. So I'm integrating sine cubed and you know what we're going to do? We're going to do that kind of same thing we did on the quiz. We're going to let u equal the other trig function when you have powers of sines and cosines. I'm going to let u equal cosine. I know it's weird, but I am. I know I don't have a cosine. But you could write it so you did if you want to. You could rewrite this as the integral from 0 to pi over 6 of sine squared. There's my sine squared times sine. So now I'm going to let, sure, there's never enough room. So I'm going to let u equal cosine theta. So u is cosine theta. Du is negative sine theta, d theta. So negative du is positive sine. And then I should also change my limits of integration again. So if theta is 0, u is cosine of 0, which is 1. And if theta is pi over 6, u is cosine of pi over 6, which isn't 1/2, because that's what sine of pi over 6 is. It's root 3 over 2. Whew. All right. So this is then going to end up being 1 minus u squared. Sine of theta d theta is negative du. From 0 gives me 1. Pi over 6 gives me root 3 over 2. Now there's a nice thing we can do here that you don't have to do. But since these limits of integration are kind of out of order, right, the bigger things on the bottom, the smaller things on top, we can change the order and drop the negative sign. So we can say this is the integral from root 3 over 2 to 1 of 1 minus u squared du. Finally, I should have picked a different limit of integration. Oh well. I integrate, I get u minus u cubed over 3 from root 3 over 2 to 1. And fortunately, I don't have to go through the whole process of going back to theta and then back to x to get the original variables. I just get to plug in my transform limits of integrations. I get 1 minus 1/3 minus root 3 over 2 minus root 3 over 2 cubed over 2 over 3. Which I definitely would not simplify. We've done enough. So as you can see, these problems can be quite lengthy. Let's do, they can be so gross. I was trying to grab a couple more that I think are worthwhile. I guess, I mean, I could talk all day about trig substitutions. But I feel like I should dedicate some of our class time today to partial fractions. So we will definitely revisit all of this again next week. But I do feel like, yeah. Oh, I know what we should do. We should do one more. Yeah. So what if I have an integral like, sorry, I want to make sure this doesn't come out terribly. let's just make it not terrible. 1 over x squared plus 16x dx. Interesting. You actually have a couple options here, I think. Well, I know of one option anyway. Ooh, yeah. No, actually, I'm a liar. We do not have a lot of options here. This one would actually require partial fractions, which we haven't talked about. So let's talk about partial fractions. So partial fractions is really just an algebraic method of rewriting an integral into pieces that add up to that integral. And the process starts by observing two things that have to be true. Thing one, you have to have a rational function where the degree on top is strictly less than the degree on the bottom. It can't be equal. If they're equal, you have to do something else first. Thing two, the bottom has to factor. Those things have to be true. It can factor minimally, right? Like it can factor just a little bit, but there has to be some amount of factoring. So I can rewrite this integral as the integral of 1 over x times x plus 16. I was thinking I was going to have to complete the square here, but that's not the case. We'll talk about completing the square in a moment. And then our job is to do some algebra. And the algebra is going to be that 1 over x times x plus 16 is equal to a over x plus b over x plus 16. Because if I get a common denominator over here, right, if I multiply this by x plus 16 over x plus 16, and this by x over x, I'll get a times x plus 16 plus b times x over x times x plus 16, and that'll equal 1. And then I can just figure out what a and b have to be to make that true. The easier algebra, of course, is just multiply both sides by the denominator. So typically, after we do this, we take the step of multiplying everything by the common denominator x plus 16 times x. On the left-hand side, we always just get the numerator. On the right-hand side, when we distribute this, this times this cancels the x. So you get a times x plus 16. This times this cancels the x plus 16, and you get b times x. And now, here's the thing. These things are supposed to be equal no matter what the value of x is. This side equals this side for any value of x. Specifically, I'm going to pick some convenient values of x. I'm going to pick x equal to negative 16, because that makes this part 0. And then I can see that, oh, if x is negative 16, well, I still have 1 on the left, right? Nothing has changed on the left. And I have b times negative 16 on the right. So b is equal to negative 1/16. And then I can do the same thing. I can pick 0 for x. If x is 0, I get 1 equal to a times 0 plus 16. Plus 0. So a is equal to 1/16. So it is in fact true that this expression, 1 over x times x plus 16, is in fact equal to 1 over 16 over x minus, I'm going to write it as minus 1 over 16 over x plus 16. These two expressions are completely equal for any value of x. And that means if I want to integrate this one, I can just integrate that one. So I want to find the integral of 1 over x squared plus 16x. I'm going to write it as the integral of 1 over x times x plus 16. And then as the integral of 1 over 16 over x minus 1 over 16 over x plus 16. And I would probably factor out the 1/16 since they're the same. So it's the integral of 1 over x minus 1 over x plus 6. Well, great. We know how to integrate those things. the integral of 1 over x is the natural log of the absolute value of x. And the integral of 1 over x plus 6 is the natural log of the absolute value. Sorry, that's x plus 16, not 6. Is the natural log of x plus 16 in absolute value. And I will mention here that a lot of times you'll see people simplify this. When you've got a natural log plus or minus another natural log, we often combine them and write this. In this case, it's 1/16, the natural log of the absolute value of x over x plus 16. Kind of cool. So, partial fractions, again, come down to this idea of you have to be able to factor the denominator, and you also have to be able to, well, first, the degree on top should be less than, not equal to, less than the degree on the bottom, and then secondly, you have to be able to factor the bottom. Someone had asked, and it's a fair question, how I did the polynomial division on the quiz that I posted, because it didn't actually show the polynomial division. I showed an alternate way of solving it because typing division is hard. So the question on the quiz was how to integrate x cubed over x minus 2. And this actually does come up when you're talking about partial fractions as well. So when your degree on top is greater than or equal to your degree on the bottom, you have to do polynomial division first. So if we do the division here, so first of all, I need to fill in the missing terms. I need a 0x squared, a 0x, and a 0. For this particular example, you can do synthetic division because the denominator is a linear factor. But if your denominator was like x squared minus 3, you couldn't use synthetic. So you should still make yourself sure that you're comfortable doing long division, polynomial long division. But then we just do, what do you multiply with x to get x cubed? Oh, it's x squared. X squared times x is x cubed. X squared times minus 2 is minus 2x squared. And then we subtract. That minus that is 0. That minus that is positive 2x squared. Bring down the next thing. Repeat the process. What do you multiply by x to get 2x squared? 2x. 2x times x is 2x squared. 2x times negative 2 is minus 4x. Subtract, just like regular division. That minus that is 0. 0 minus minus 4 is positive 4x. Bring down the 0. X goes into 4x 4 times. 4 times x is 4x. 4 times negative 2 is negative 8. Subtract 0, positive 8. And x doesn't go into 8, right? X has a higher degree than 8, so we're done. That's our remainder. So this is equal to the quotient, x squared plus 2x plus 4, plus the remainder over the divisor. And then you can integrate this. I don't want to integrate it. I think you all can integrate this just fine. Let me show you one trick question, just because I think it could come up. It's real easy if you know how to do it. Okay. We could, if we wanted to cause ourselves great pain, do trig substitution here. You could totally let x equal tangent theta and then do the whole work. It's not fun. Typically, I usually refer to trig substitution as a method of last resort, but usually it's pretty obvious when you have to use it. Typically, with rare exception, you almost never use trig substitution unless you actually have a square root or some sort of root somewhere. There are exceptions, but 9 times out of 10, 99 times out of 100, you're really not doing trig substitution unless there's a square root of a 1 plus x squared or an x squared minus 1 or whatever. Or a 3/2 power or something like that. There is like one exception I can think of. In this case, you could do a trig sub, but you could also do polynomial division. right? The degree on top is equal to the degree on the bottom. So what is x squared divided by x squared plus 1? Well, when you multiply by x squared to get x squared, 1. 1 times x squared is x squared. 1 times 1 is 1. Subtract 0. 0 minus 1 is minus 1. So this is equal to the integral of 1 plus negative 1 or minus 1 over x squared plus 1. And although I will fully admit you can sometimes have to use trig substitution, this is a known function whose antiderivative that we know. Or we know that the antiderivative of 1 over x squared plus 1 is the arctangent of x, or the inverse tangent of x, which you could also find via trig substitution, but you don't have to. So we can just say, oh, hey, look, I get x minus the arctangent of x. Easy peasy. That's it. Or you can make your life real hard and do x equal tangent theta, dx equals secant squared theta, d theta. Okay, I think this is really stupid. Really challenging. You get the integral of x squared to tangent squared, and then dx is secant squared. Yeah. And then on the bottom you get, you get 1 plus tangent. You get 1 plus secant, 1 plus tangent squared, which is secant squared. You could do it that way. How do you integrate tangent squared? The way you integrate, so this could come up. Tangent squared is another. This is like a doubly trick question. One, it's easy if you do it that way, but if you don't do it that way, you get to here, and then this. Did I forget to square it? I might have forgotten to square it. I don't think I forgot to square it. So I'm doing the trig sub. X is tangent. X squared is tangent squared. Dx is secant squared. And 1 plus tangent squared on the bottom is secant squared. So now I think I'm good. I think I'm right. So then the question is, how do you integrate tangent squared? This is most calc teachers, one of their favorite trick questions. It is super easy if you know the trick. You guys all know the trick. You might just not know that you know it. The trick is you know a trig identity. You know that 1 plus tangent squared theta equals secant squared theta. So you know that tangent squared theta equals secant squared theta minus 1. And you know that the antiderivative of secant squared is tangent, and the antiderivative of 1 is not x, it's theta because we're using thetas. And then tangent theta equals x. Theta is the inverse tangent of x. Same. I wouldn't do it this way. I would do it this way. But you could do it either way and still get to the right answer. Okay, so the point I was getting back to was that sometimes before you can do anything else, you have to do polynomial division. I don't want to just make something up. That's always a recipe for disaster. Let me grab an actual problem here so I don't make up some super garbage stuff. Where are all my examples? Where are my partial fractions? There we go. That's not partial fraction. Oh, okay, fine. That's partial fraction. Yes. Okay, fine. I'll make some stuff up. Let's do this. Let's find. Okay. Yeah, let's do the integral of x cubed over x squared minus x. This could be heinous. That's all right. So good practice. So before we can do anything else, I recognize that the degree on top is larger. I have to do polynomial division. I should say, you have to do polynomial division if you don't see some easier method, right? Like if there's maybe a really super obvious U-sub, you should do that. If you don't see anything obvious, division. So x squared minus x into x cubed plus 0x squared plus 0x 0. Multiply this by x. X times x squared is x cubed. X times negative x is negative x squared. Subtract. 0. 0 minus 1 is 1. 1 times x squared is x squared. Subtract. That minus that is x. And that's our remainder because x squared is a higher degree than x, so we can't go to that. So we can rewrite this integral as the integral of x plus 1 plus the remainder. I picked a dumb problem. I'm really dumb. Why is this really dumb, James? Because I could totally cancel but factor out an x on top and an x on the bottom and cancel an x. Okay, I'm gonna fix it. I'm gonna fix it like Fix It Felix. I really enjoy Wreck-It Ralph. It's a good movie. I'm gonna make this x cubed plus 2, so that there's a plus 2 over here, so that we couldn't just factor and cancel out an x. Okay, fixed. So it's x plus 1 plus the remainder x plus 2 over x squared minus x. And then we're going to have to iterate this. Now, be careful. This is going to require integration by parts, but sometimes people try to be real clever, and they're like, I'm going to make it so, maybe let's pretend like, just for a second, that we did this division, and instead of getting x plus 2, we got 2x minus 1. And so our integral was x plus 1 plus 2x minus 1 over x squared minus x. We can integrate x, we can integrate 1. Do you guys see anything that we could do for 2x minus 1 over x squared minus x that doesn't require partial fractions? Like maybe a U-substitution? Right, if u is x squared minus x, du is 2x minus 1. So not that that's what's happening in this particular problem, but I've definitely seen people write problems like that so that when you get to the remainder part, the top is like exactly the derivative of the bottom, so you can just do a U-sub for that. That's not what we have here, but it does happen sometimes. So we've got this. We've got the integral, and I'm going to write it, the integral of x plus 1 dx plus the integral of x plus 2 over x squared minus x. This part's easy. This is just x squared over 2 plus x. This part we have to work on. So we're going to do the partial fraction decomposition. So x plus 2 over factor the bottom. And then we write out it's equal to constant over the first factor plus constant over the second factor. Now, we're not going to get to it today, but there are definitely other things that can happen with partial fraction decompositions that are more complicated than this. Maybe we can probably fit in one problem in a second. Multiply both sides by the common denominator. So this, you just get the numerator, x plus 2. Here you get a times x minus 1 plus b times x. Pick convenient values. And when I say convenient values, I mean values of x that make one of the terms 0. So pick x equal to 1. Unlike the previous problem, now we have places to plug it on the left side too. So if x is 1, I'm going to get 3 on the left. I'm going to get b times 1 on the right. So there's b. Pick x equal to 0 so that this part cancels out. I'm going to get 0 plus 2 equal to a times negative 1. So a equals negative 2. Great. I'm going to erase the polynomial division, so enjoy it while it lasts. I'm going to rewrite this as x squared over 2 plus x plus the integral of a over x plus b over x minus 1. So a is negative 2 over x plus b is 3 over x minus 1 dx. And now the rest of this is not terrible at all. This is x squared over 2 plus x. The integral of negative 2 over x is minus 2 natural log of the opposite value of x. The integral of 3 over x minus 1 is 3 natural log of the opposite value of x minus 1. And if the coefficients of the logarithms are different, we usually don't try to put them together. All right, we can definitely fit in one more. So, if you have a rational function with the degree on top is strictly greater than or equal to the degree on the bottom, you should most likely do polynomial division. But what if we were trying to integrate something like, let's not make it too awful, James. Let's make it x squared plus x plus 1 over x to the 4th minus x squared. He says try not to make it too awful and makes it really awful. That's not awful. Okay, the degree on top is less. Check. Can't do a U-Substitution, right? Like if you let U equal the bottom, the derivative is definitely not even close to the top. So you should always kind of check for a U-Sub, right? If someone gave you this problem, yeah, you could do integration by parts. Sorry. I always say that when I mean partial fractions because they both have the word part in them. You could do partial fractions here, but you really shouldn't because the derivative of the bottom is just the top. So here you should do u equals x to the 4th minus x squared. Du is the top. This is the integral of du over u, which is just the natural log of the absolute value of u. So you should always be on the lookout for those easy u substitutions because if they're there, they're usually nice. That's not what we're going to have here. So in this case, we have to factor the denominator as much as possible. And I should emphasize there, as much as possible. So first I can factor out x squared, and I get x squared times x squared minus 1. But then the x squared minus 1 factors further as x minus 1 times x plus 1. Okay, here's how the partial fraction decomposition is going to work. Anything that's raised to a power higher than 1, you get all the lower powers as well. So I have to say I'm going to have a over x squared, and then need lower power of x down to 1. So I also need a b over x. I have a c over x minus 1, and a d over x plus 1. Fun times. Let's erase this. I don't need this anymore. So then we do the same usual thing of multiplying both sides by the denominator. On the left, I'm going to get the numerator, right? That's always going to happen. So I'm going to get x squared plus x plus 1. I'll have terms too. And then on the right-hand side, we have to see what cancels. So when I multiply this by x squared times x minus 1 times x plus 1, the x squareds cancel. So I get a times x minus 1 times x plus 1. And then when I multiply all of this denominator by b, I get b times x minus 1 times x plus 1. And then when I multiply this term by all that, the x minus 1s cancel. So I get c x squared times x plus 1. And then I multiply this by all of the denominator, I get the x plus 1s canceling. So I get d times x squared times x minus 1. Whew. Okay. We've got a lot of convenient values to pick. X equal to 0, x equal to 1, x equal to negative 1. If x is 0, I get 1 on the left, and I get this is 0, this is 0, and this is 0. So I get a times negative 1 times 1. So negative 1 equals positive a. Great, a is negative 1. When x is 1, this is 0, this is 0, and this is 0, I get this. So when x is 1, I get 1 plus 1 plus 1 equal to c times 1 times 2. So 2c. So c is equal to 3 halves. when x is negative 1. On the left, I get 1 minus 1 plus 1, so I get 1. On the right, this is 0, this is 0, this is 0, this is not. I get d times 1 times negative 2. So I get negative 2d. So I get d is negative 1/2. And finally, I've run out of convenient values. If there are, and this is always going to happen when you have a repeated factor, right? When you have a factor that's to a power higher than 1, you're going to run out of convenient values. And there's a couple options. If you only have one thing left to find, you can literally just pick any other value of x, plug in what you know for a, c, and d, and solve for b. This is not my preferred method. Because even though it's not hard, it's still not like super easy here. Right, like I could pick x equal to 2, and I'd have 4 plus 2 plus 1 is 7 over here. And then I'd have negative 1 times 3 plus whatever b is times 2 times 1 times, right? It's just like, ugh. The method I am partial to, pun intended. That pun was definitely intended. The method I'm partial to is, I mean, it wasn't thought of ahead of time, but I was like, oh, this is going to be great. The method that I like is the method that's called equating coefficients, where this is a polynomial. So is this. For polynomials to equal each other, the coefficients of each power of x have to actually be the same. So on this side, I have no x cubes, right? There are 0 of them. On the left side, there are 0 x cubes. On the right-hand side, though, if I multiply this out, and I don't really want to multiply it out, but if you did, right, this would be a times x squared minus 1. So you'd have ax squared minus a. Here you'd have x squared minus 1 times another x, so you'd have x cubed minus x times b. Here you'd have c times x cubed plus x. Here you'd have d times x cubed minus x. So you can see that on the right-hand side, the coefficient of x cubed would be b plus c plus d. And the amount of x cubed on the left has to be the same as the amount of x cubed on the right. But look, I know that d is negative 1/2 and c is 3/2. So I can say that 0 equals b plus 3/2 minus 1/2. 3/2 minus 1/2 is 1. B plus 1 is 0, so b equals negative 1. I like this method the best. I think it works great. Okay, so now we've rewritten our thing as, let's write it up here. So I've got negative 1 over x squared plus negative 1 over x, so minus would be the smart way to say that, minus 1 over x plus c plus 3/2 over x minus 1 plus negative 1/2 over x plus 1. And all of these can be integrated really, really easily. I don't know where to erase. I guess I'm going to erase right here. So negative 1 over x squared, I would probably rewrite as negative x to the minus 2. So when I integrate this, I get negative x to the minus 1 over minus 1. That's just 1 over x. And then the rest of these are logarithms. Minus natural log of the absolute value of x, plus 3/2 natural log of the absolute value of x minus 1, minus 1/2 natural log of the absolute value of x plus 1, plus c. So the whole idea here is that by this partial fraction decomposition, you're going to make the thing you're trying to integrate much easier to integrate. All right.